is a mini lecture on categorizing immunity. So we define immunity as our body's ability to combat diseases, infectious disease, and cancer. And there are two ways that immunity can be classified. And just like with our discussion of epithelial tissues, where you always use two descriptive terms to describe a particular epithelial tissue, with immunity you always use two descriptive terms. So immunity can be natural or artificial, and active versus passive. Right. And this graphic is just pointing out that you can have natural active immunity, you can have natural passive immunity, artificial active, and artificial passive. Right? You definitely, for the quiz and for the next exam, you're going to want to be able to look at examples of or descriptions of immune reactions and use these labels to categorize the response. So what's active immunity? Well, it's defined by our own body producing antibodies against a specific antigen, right? So to be considered active immunity, your body's B cells have to make antibodies. You yourself have to generate the reaction. Right now, that can be natural active immunity, which would be an example of that would be being infected with some sort of pathogen, or it could be artificial, right? Immunization. One thing I want to caution you guys about is you definitely don't want to fall into the trap of thinking that because something is natural, it's automatically better than something that's artificial. We talked about this a little bit in class the other day, right? You can have natural active immunity to the varicella virus that causes chickenpox, or you can have artificial active immunity because you've been immunized against that virus. For a virus like the one that causes chickenpox, once you have had an infection, that viral DNA is always in your body. And as you age, it can be reactivated and lead to a disease called shingles. That's not possible with the vaccine for chickenpox. So underlying active immunity of whether it's natural or artificial is an initial exposure to an antigen that results in a fairly short and fairly slow response, but with a secondary response that's quite rapid and quite strong. Active immunity is generally long-lasting. As long as you have memory B and T cells that have interacted with the antigen either in the vaccine or from a pathogen, you will be immune. This graphic is just showing the time course of antibody production. So initial exposure either to vaccine or to pathogen, the primary immune response is the adaptive immune system's initial response, and you can see secondary exposure, right? The primary immune response that never goes away completely because you still have antibodies because you've been exposed to it, right? So if you've ever been exposed to the bacterium that causes tuberculosis, if you have a skin test, you're going to test positive because you will have an immune reaction. Doesn't mean you have tuberculosis. After a secondary exposure, you have a secondary immune response that's much larger, and if you look at the slope of these two lines, right, the slope here is much steeper. Passive immunity is sort of what it sounds like. You're given prepared antibodies or immune cells from someone else in order to combat disease. Now, because your own body is not making the antibodies or generating clonal expansion of your own immune cells, the effects are going to be temporary. Some examples of this kind of immunity, naturally acquired passive immunity, would be antibodies that cross the placenta that protect fetuses and newborns from certain pathogens, antibodies that are present in breast milk that the mother produces, and then we can also give injections of antibodies. Antivenoms for snake bites or spider bites are often antibodies. All right, so to sort of sum up the distinction between the innate and adaptive immune systems. The innate immune system is nonspecific in its response. The adaptive immune system has an antigen-specific response. The innate immune system has an immediate maximal response, whereas with the adaptive immune system, there's a latency, a lag time between exposure and maximal response, right? Even with the primary exposure to a pathogen, there's going to be a lag time for the adaptive immune system because it takes time to go through that whole process of phagocytosis, antigen presentation to the T cells, clonal expansion, or activation of B cells and clonal expansion. The innate immune system is literally innate. It's inborn. You come into the world with it. Whereas the adaptive immune system develops for a particular person in response to specific environments. The innate immune system has no mechanism for memory. So you're not going to have a greater response the second time you get a splinter in your foot, for example. That's not true with the adaptive immune system. Exposure to antigens leads to immunological memory, which then leads to heightened response and more rapid response after a second exposure. So this is the concept map that I put up the other day, sort of fleshed out a little bit, adding some details about the protective proteins and the process of phagocytosis and the inflammatory response. In this slide, we just have another summary looking at the first, second, and third lines of defense in the immune system. This graphic shows an overview of the first line of defense, which involves physical, chemical surface barriers. So lysozyme in saliva, tears, sweat, intact cutaneous membrane, that is skin, intact mucous membranes, acidic stomach, acidic vagina, for females. Commensals, that refers to the barrier that's provided by a healthy lawn of symbiotic microbes on our skin. And then finally, just another way of kind of organizing the information about innate and acquired immunity, showing the first, second, and third lines of defense.